The next time is going to be deuterium fractionation. The talk is given by Paola Caselli.
Okay. So I am going to present work done in collaboration with Cecilia Ceccarelli. This is me from University of Leeds, Dominique Boclin-Morvan, Olivier Motsis, Sandra Pizzarello, François Robert, and Dimitri Semenov. This has been a very interesting adventure, I have to say, and the reason why I'm putting here Labyrinth and the reason of the title is that at the beginning, and I think even now, things have been a little bit complicated in a sense that, as we will see, it's not so easy to talk to different communities, but we feel strongly that it's really, really important to not just talk, but do more than that, okay? So now here is like a list of objects, beautiful images showing basically our astrochemical heritage, going from molecular clouds to star-forming regions, to protoplanetary disks, to our solar system, and finally to us that you don't see here, but that is in fact a little dot seen by Cassini, and that is where we are. Actually, we are here. If I was not so nervous, I should actually point at that. So the other thing that we have this pressure objects that fall down, these jewels that come down from the sky, history raining every day, and this is great. I mean, where else we can have so many and so important information? Now, this is the structure of the chapter, not of my talk, so don't be afraid. So we go from setting the stage, so we describe the chemical processes, the deuterium fractionation processes, then the brief history of the solar type system, from prestellar core, so just before stars are born, to protostars, protoplanetary disk comets, and then we go into the carbonaceous chondrites, interplanetary dust particles, or IDPs, with their clays, minerals, insoluble and soluble organic matter. We will talk about, we will write about the 15N, not talk about today, there is no time. And then finally, we will make some summaries and talk about the solar nebula models. Just to set the stage a little bit, here is a figure coming from the review paper that I have wrote with Cecilia Ceccarelli, where it is shown 4 or 5 of the steps that we have to consider if we really wanted to link ourselves to the molecular clouds. So we start from the prestellar phase, where we have formation of simple but also complex organics, molecules, and where the mantles of dust grains start to become thick, rich of water, and also organic molecules. Protostellar phase, where we have partial sublimation of this ice, and also chemistry, hot chemistry shocks, so a very violent environment, to the protoplanetary disk phase, where we have dust coagulation, gas and ice processing, and then finally the planetesimal formation, and finally the rain onto the Earth, and maybe the delivery of some of the pristine material, or even the pristine material that has been processed, but still, I think this is one of the points. It is important to take into account this pristine material, maybe. So some basic questions that actually were at the base of our interest of joining forces with other community is simply, are there clear links between our solar system and star planet forming region? Can such links help us to better understand our origin? And at the same time, of course, we also want to help the other community and say, can such link help to better understand the chemical and physical processing in star and planet forming regions? Just to point out again that we have really 2 treasures now. With all the data that we can gather for star and planet formation, things, of course, are going to get better and better. And the fact that we have a very detailed measurements for our solar system bodies, then it is really time to start to work together for a full exploitation of these treasures. So my outline will go through relatively quick deuterium fractionation processes, then go through the observational evidence in prestellar core protostars, these comets, meteorites, and IDPs, trying to find some commonalities, and then I will show the summary, unrolling the thread, and of course some of the things to do, because there are really lots. So deuterium fractionation processes. Before that, there are the first thing that we thought with Cecilia to be really important is to build up a dictionary. I'm not going to show you all the dictionary, of course, but this is really important to speak the same language, or at least understand, okay? We are not pretending that one of the two communities start to speak in different. So one of the important things is, for example, as we have seen in the previous talk, is the D over H that we measure. For a solar system community, this is typically we use this delta D in per mil, and this is a relative value to the so-called D over H, not even SMO, as we see before, but VSMO. What is VSMO? It's the Vienna Standard Mean Ocean Water, and this refers to the evaporated ocean water, okay? Just to give you an idea. So this is probably the first page of our dictionary. For the chemistry, the first two steps, first of all, you have to form molecules, so molecular hydrogen, and molecular hydrogen forms on the surface of dust grains. Once you have done that, then really the fun starts, because then you can produce H3+, that is the first step toward molecular complexity in the interstellar medium. So you have cosmic rays hitting H2 molecules, and 97% of these forms H2+, which then react again quickly with H2 molecules because they're very abundant in molecular clouds and form H3+. Now, don't be scared. This is not so complicated. Just follow me, so that don't see everything together. Start from this. So this is where we left from the past slide. Cosmic rays form H3+. Now these H3+ can actually give a proton to other species and form, for example, say, precursor to important and easy to observe molecules like ammonia, formaldehyde, HCO+, or dissociatively recombine with electrons and form hydrogen or molecular hydrogen. However, if it encounters HD, and HD is about 10 to the minus 5 compared to H2, as we've seen in the previous slide, that is the cosmic abundant, then it can form H2D+. And this reaction, if the temperature is low enough, say lower than 30 Kelvin, it typically proceeds from, say, left to right, because it is exothermic, and in these cold clouds, where the temperature are typically 10 Kelvin, it's very hard to go back. There are some exceptions, but there is no time to go through these exceptions. So then you can actually keep going and form even more deuterated forms of H3+, so D2H+ and D3+. These, of course, can give the deuterium to the species that we encountered before, and now you can form DCO+, deuterated ammonia, and so on and so forth. There is another important step, which is the step 3, that comes from the fact that when you enrich a lot the gas phase of these molecular ions, deuterated ions, when they dissociatively recombine, they enhance the D over H ratio above the cosmic abundance. So you get the D over H ratio that can go up to 0.3, 0.5. And this, of course, means that the deuterium can compete with the hydrogen to deuterate the atoms and molecules that freeze out on the surface of these dust grains. Some little things that it's important to bear in mind: freeze out of neutrals boosts the diffractionation, and this has been known since '86 by Dalgarno and Lepp. Diffractionation slows down if ortho to power H2 ratio becomes larger than a certain value, because this can drive back this reaction because of the higher energy of the ortho H2. Lots of the literature, Flower et al. Discussed this in particular, but this goes back to Gerlich et al. 2002. Importance of H2 tunneling reactions on the surface. Okay, so now routes to water deuteration, I'll just mention briefly, because otherwise I'll probably lose everybody here already with all this chemistry. So first of all, on the surface of cold grains, these things can happen because we have the hydrogenation and, of course, also the deuteration of oxygen, O2 and O3, and these can give HDO. And water, of course. In the gas, we have the DH exchange that can happen both in the cold, through the H2D plus, in slightly warmer gas between 30 and 100, through slightly more exothermic reaction that form the CH2D plus. In hot gas, OD, this is a very nice paper by T et al. That show this, that you can form deuterated water even at 1000 Kelvin in the gas phase, and very hot, where you can start to have the exchanges also back in the hydrogenation. The overH exchange in the ice, if the temperature of the dust becomes close to sublimation, there is a transition phase in which your ice start to become a little bit mobile, and you can actually activate lots of reactions. And this is when you form other molecules, but also exchange hydrogen and deuterium. Okay, so let's go through now some observations. This is one of the Prestellar cores that we have studied in detail. So one thing to say here is that to bear in mind, so these are regions that are precursor to star, probably single stars. We don't see for now much fragmentation in the central region. This is about, say, 1000 AU, this bright peak in the continuum, dust continuum emission, a millimeter wavelength. What we see is a clear absence, or say what we call depletion, or if even better, freeze out, because we know that the CO is freezing out on the surface of dust grains. A region of this depletion zone of the CO is about 7,000 astronomical units. Then if we look at the deuterated molecule and compare with the non-deuterated molecules, like for example N2H+, it is clear that the diffraction increases toward the center, where the CO gets more and more depleted. And the D/H ratio that we get from these molecules, it becomes 0.2. So it's orders of magnitude above the cosmic D/H ratio. Just some more number that, of course, many other authors and papers in the literature, these are just some of them. Just to show you some of the big numbers that have been found, Laurent Pagani in another Prestellar core, in deuterated ammonia, and very recently by Silvia Spezzano et al. Found the doubly deuterated cycle form of C3H2, and with relatively large values. Right, so H2D plus being the main driver is of course abundant, and in fact the line that we detected 10 years ago was 1 Kelvin, almost 1 Kelvin line. That was very kind of a surprise at that time. So we had to remake the models, include all the doubly deuterated and triply deuterated H3 plus isotopologues. And it's not just that, it is extended. So we found this 5,000 astronomical unit extension of the H2D plus, work by Charlotte Vastel et al. Not just the ortho H2D plus, but also the para D2H plus, which is even harder to see because it's above 600 gigahertz, the frequency, so it really needs apex to observe. So here we have extended emission of the para D2H plus line. Even Alma can see it, and this is work by Rachel Friesen in preparation, where we see actually a little tiny 400 times 200 astronomical units. This is a Prestellar core, and work in preparation, so I'll ask Rachel, who should be here, still about all the details. Little summary for this Prestellar cores. So we can actually very roughly separate them in 3 zones. One is the outer edge, where we have still the photochemistry important. So you have the photons that some kind of partially dissociate your molecules. The dust grains don't really are not really covered by ice mantles because, again, photons can photodesorb the water, so you start to have a little bit of water on top. Then if you go in the dark cloud zone where the CO is not yet significantly frozen onto the dust grains, this is the place where you start to have this thick water ice mantle formed by the hydrogenation of, as we saw, oxygen on O2 and O3, but also you start to have CO, CO2, and ammonia. Everything that can be hydrogenated fast can be done on the surface. And then if you go in the deuteration zone, so we predict and we think that these ice mantles become significantly large, probably a significant fraction of the radius of these dust grains, original dust grains. Okay? So this is all, say, initial conditions. So what happened in Protostar? This is one of the beautiful pictures from Hubble. Well, here you have, of course, to understand that if you look in the optical, we don't see much. So I had to put a little artistic impression here to show what's going on in the center. So you can imagine that once the protostar switches on, things becomes a bit more complicated because you have, of course, the heating of the protostar. You have the shocks from the outflow lobes that are driven by the protostar, and all these things can, in a sense, reprocess already. Our dust grains, you can have, of course, a thermal evaporation, maybe partial, not total. There is some evidence of that. There is also the sputtering, the vaporization of dust grains along the jets and outflows. So all these things can affect, of course, the chemistry. What do we see? Now, this plot is a little bit probably complicated, but is a way to summarize everything in one slide. So let's see if you can follow me here. So first of all, this is the first one shows the HD over XD over XH in 3 molecules only. There's otherwise too many things here. So it's water, formaldehyde, and methanol. So we have several things here. So in black and white and gray are the models run by Vianney with the gray Noble code. So here we have different temperature, 10 and 20, you see it's a slight difference, and different density from 10 to the 3 to 10 to the 6. And in color, we have the data. Now, one thing that, and here we have the XD2 over XH2, so the doubly deuterated species. So one thing that I wanted to put your attention on is that, first of all, the water that is in this part here, well, there is a little bit of some disagreement in some of the numbers, so this is probably something that we will have to work on a little bit, especially on the deuteration of the water in RS 16293. But there is like an upper limit, in a sense, of, say, about 0.1 in deuteration. Things can get much more deuterated if you go to the organic species, and we can go up to U90, very large, very efficient deuteration. Of course, there are other things that you need to look at, including Magnus Persson poster and I think upcoming paper. If I put this in another slide like this, where I show the D over H, D2 over H2, and D3 over H3 for various species, again, you see that the deuteration is much more significant in organic species. As we go, say, to more complex species, the deuteration becomes very large. We talk about 13 orders of magnitude, and for this, you should look at these papers here by Berenger, Paris, et al. And what we believe is going on, based also on the models, chemical model, is that this is showing us an ice formation time sequence, in a sense that we have the water forming first, probably at the outer edge of the prestellar cores, and then once we have the freeze out of the CO, you start to cover this water with the CO. You process the CO with the hydrogen. You form first HCO, then formaldehyde, and then you go up to as much as you can, so to methanol, okay? So these stages happen in this depletion zone, in the deuteration zone, where the D over H becomes really significant. All right, for the deuterium fraction in protoplanetary disk, this is just a pretty picture to show. what I have here is probably not as pretty, but it summarizes basically all what I want to say here. So if we consider, here I made a big jump, because I went to the phase, say, of, say, class 2 stars, so the protoplanetary disk. Here we don't have much accretion from the envelope anymore. We have the so-called naked disk, and we have something like small grains everywhere, gas everywhere, but we start to have some agglomeration and condensation of solids. And what it shows here is several layers of this disk. So we start from the ionized atmosphere, where the temperature of the gas is large, and we have mostly photochemistry going on. Then we have the molecular layer, where photons, so you are now UV screened there, so molecules can survive and thrive, and we have a temperature between 25 and 100 Kelvin. And then to reach conditions, say temperatures that are similar to the ones that we have, say, in the Prestellar cores, we have to go to the mid-plane, and here is where we believe the heavy deuteration is going to happen, and of course the freeze out of neutrons. Of course, these things here can be reprocessed by interstellar and stellar UV photons, as well as X-rays. So we predict that, and the models predict that above, say, this of course depends on the star that you have in the center, but say above, say 20 astronomical units for typical, say, Deuterium stars, we have like probably a survival of the ISM deuterated species, while if you are closer to the star, there is some deuteration reprocessing, and these are the predicted molecules that can actually survive better in this region. Where here we can find the similar species to Prestellar cores. Now, this is one of the, say, first papers showing that actually this is actually happening. This is the paper by Karin Oberg et al. 2012 from TWI observation, putting together the science verification data from ALMA and SMA, so showing that DCN, which is in fact is predicted to be abundant in a slightly warmer gas than the DCO+, shows a nice peak in the center of this protoplanetary disk, while the DCO+ shows a little bit of a gap. Now, if I show you this, now I guess you are even more convinced. I thank Paola Caselli, who sent me the final figure a few days ago. This is a paper that is just on AstroPH, so a few days ago, so please have a look. Amazing ALMA imaging of the CO snow line, because this is where CO is, of course, partially, but significantly depleted, frozen out, and you see this nice ring and the large deuteration. This large number I'd never seen before in disks. And this is, the ring is between 110 and 160. This is actually a Herbig AE star, so it's more luminous than the star that was in the sketch that I just showed you before. Let's go to comets. And, well, this amazing picture. And now talk about probably the most important result that we had in the last few years, and thanks this to Herschel. This is a press release that you can find at this website showing the Hartog et al. Result, who measured the H2O and HDO toward the Jupiter family comet. This is very important because for the first time it was measured in a comet, the D/H ratio in water that is exactly the same as Derek List was saying before, as the D/H ratio measured in our oceans. So again, it's a little bit, started several debates. One of them is that, as we heard from the previous talk, we thought the comets maybe were not important contributors of the water to the Earth, but now these values, of course, change things a little bit. And there were also some more measurements from Herschel also in a Oort cloud comet, finding this 2 times 10 to the minus 4, and also some new measurements of the Halley, d over h in water, that push down the value there. Okay, more thing that I wanted to point out, and this is important to as we will see, to unroll the thread, is that it's important to remember that this d over h ratio that looks not so high compared to what we see in star-forming regions, well, there is evidence in comets, unfortunately not as many as I'd like to, but there is evidence that DCN, so let's say the deuteration in organics, is 10 times larger than the HD over H2O. And this reminds me something. That reminds me the star formation place. So these are unfortunately upper limits. So this is something that I'd really like to see more measurements here. Deuterium fractionation in meteorites. This is one of my preferred pictures for that, the oldest piece of our solar system. And what we want to concentrate here, because of course to make the links with the chemistry in the interstellar medium, are these organic rich meteorites that are called carbonaceous chondrites, and we will in particularly focus on the matrix that hold together these nice chondrules and other stuff. This matrix can be roughly divided in 2 parts. One are clay minerals, so hydrous minerals that have been basically formed and experienced some liquid water, and so, but they are minerals. And on the other side, we have organic matter. And let's go a little bit in more detail. We have some measurements of these carbonaceous chondrites that shows very interesting numbers. One is that, for example, for the hydrated silicates, so these clay minerals, etc., we have D over H ratio that are very similar, and this was already said in the previous talk, to the ocean deuteration. So this is the deuteration of water. Now we go back to the organic molecules, and what we find? Well, we find, again, the same trend. We have the D over H that is typically larger than that, and it can go up to 1% here, which is getting very close to what we see in the interstellar medium. But this happens in very tiny micrometer-sized hotspots that are seen within the matrix of these chondrites. Just a little bit, you will find all the details in the chapter. So I don't need, fortunately, because I don't need to go through the details. But I thought that it's actually quite interesting. I found this fascinating to see the organic matter you can divide in two parts. You know, there is the insoluble and the soluble organic matter. And this one here, although it resembles some kind of PAH, it does not, okay? It's a very quite different structure with lots of functional groups, more complicated, and typically smaller in size than in pH that we see in material. But you see, we have aromatic structure, so these circles of carbons and hydrogen intermixed with other elements and molecules. The soluble organic matter is the whole, place where you can find the rain of amino acids and even more complicated molecules and even nucleobases have been observed there. And these are just some of the amino acids that have been discovered there. These symbols here, every time you see something that doesn't have anything and the kink, it's just the carbon. It's obvious, no? Well, it should be, but it's a carbon, and then it could be an hydrogen or two, depending on how many bonds you see to fill the valence electrons. Good, so just to show a little bit what we see here. So if we look at the carbonaceous chondrites and in the clay mineral part, what we see that, first of all, a peak where the D over H in our Earth ocean is. So again, the d over h is about to say 1.5 times 10 to minus 6 or so. And then, but there is a little bit of a wing here. But look at the IDPs. There is quite similarity in this, say, shape of the curve. So these are the interplanetary dust particles that are supposed to be fragments of comets. So it's not obvious that they have exactly the same type of composition. And this is the insoluble organic matter that shows actually slightly larger deuterations. One thing to note again, and this is the recursive thing, is that the OH, so the water part, is typically always less deuterated than the more complex organic molecules. So now, what I will do, I will just wrap up things. As I said in the chapter, you will see more things, in particular the 15N fractionation that is really also another important thread to remember and study more. But for the deuteration, we decided to focus on this because, of course, of the larger number of data. So we have here a plot that shows that d over h in water in red and the d over h in organics in blue for all the say, bodies or objects that have been observed, including the latest disk DCO plus over HCO plus. So one thing that you notice here, that there is an overall kind of, this plot should be populated a little bit more, but this is part of the whole story, to find where to go and to find where really to work more. So, but there is kind of a general trend in which we see a kind of a decrease in the deuteration. And the other trend that I have mentioned all the way through this talk is that there is this difference between the deuteration of water and the deuteration of organics. So although, and again, we will discuss this extensively in the chapter about the various solar nebula models, etc. We just wanted to point out that these main behaviors that we see are very easy to make, and because of our detailed studies, especially in these simple clouds, we now understand very well what is going on. It seems they're really common. And then from my point of view, from our point of view, it's really important to try to make the link between these various phases. So some of the things to do, some of the things that I think, we think that are in particular important. So this was already mentioned also by Ted Bergin, and I also think it's really important. Bridge the gap between, at least the first step, bridge the gap between Prestellar core and protoplanetary disk. Just to answer the question, how important are the initial conditions in the physical and chemical evolution of protoplanetary disks? Also, study the reprocessing of material during the early stages of protoplanetary disk. For example, if self-gravitating disks exist in the class 0 phase, so in the very early phases, does that matter for the physical and chemical processes of protoplanetary disks that are orbiting around more evolved stars? Study protostars, study the reprocessing of material, including the dust coagulation and the chemical evolution of trapped ice that I think has not been done enough throughout the protoplanetary disk evolution, and to answer the question, which conditions favor the production of the organic material observed in our pristine? I know we are one example, but we have so much data that at least one of the models that we run, we need to understand how this material is made at some point. And then this is another point, compare protoplanetary disk models with the solar nebula models. This is so important because this will start the two communities really to merge. And of course, this is the obvious thing. We, of course, need more data to fill the plot that I showed you before. We need more theoretical chemistry. We need more laboratory work. And then finally, just go back to this iron thread that goes to us. And, with the hope, sorry for a little bit of romanticism here, but I think I'm homesick after 6 years in UK, going back to south of Tuscany. So instead of the labyrinth, this is the dream, to have one big road. This is actually, it's a very nice road, 5 kilometers of cypresses that goes to San Guido, where you can find Sassicaia wine and other goodies. So work together with all these people here and more to understand our origins. So thank you very much for your attention.
We have time for questions. In the middle, please go ahead.
Peter Voigtke, St. Andrews University. I have a question concerning the HD to H2 ratio. There's a very important paper, I think, by Ted Bergen, which you haven't mentioned, where they detected by Herschel directly HD in TW Hydra, which is a famous protoplanetary disk. And that's, of course, a very interesting thing, because the analysis is quite simple. So you have an optically thin line, so you have a direct measure of the mass. However, of course, one of the factors going into this is the HD over H2 ratio. And I wanted to ask, my impression from your talk is that it's actually highly uncertain as for bigger molecules. So for the H2 to HD ratio, is that more robust? Is there a good solid value of that that we can rely on?
Well, what we use, it's something that is based on the observations of D over H in our galaxy. You disappeared? Anyway, okay. Here, okay. So this is, but there are variations already, in our galaxy, depending on which line of sight. So there are this factor of a few difference that I didn't mention is one, say, probably of the uncertainties. There had been papers also, I think it was Bruce Train, who considered the fact that the deuterium can be locked in polycyclic aromatic hydrocarbons. All these things, unfortunately, I couldn't go very deep, but that's something that could bring us some uncertainties in this ratio. We typically take the average value, which is this 1.5 times 10 to minus 5. This is from the Oliveira paper for our say models, but it's also true that, for example, one thing that I mentioned, that was this tunneling of H2 on the surface, it could actually be depleted in the very center of this Prestellar cores. And this is a little bit more detailed, so if you want, we can talk more about that, because I guess I'm getting into too many details. But the answer is, it's not a fixed number.
Very good. Please go ahead.
Great talk. Hello, hi, this is Feng Tian from Beijing, China. Nice talk. It's really eye-opening to see that the D2H ratio in organics is really that high, much higher than that in water. But in terms of total mass, the organics is probably much less than that in water. So how will the high D2H ratio in organics contribute to the D2H value measured in the Earth's ocean? So that's a question.
Right. Okay. I don't think that the D over H ratio in organics contributed to the D over H ratio in the water. It's just what I have been showing is that there are different mechanisms, and what we believe, or at least what we understand in our simple chemistry, simple clouds, is that the reason why water is not so highly deuterated is because it is formed in an epoch during the formation of the Prestellar cores and then the star, where there is not much D over H in the cloud, okay? And then the deuteration of the organics happens later. There could be some exchange. This was one of the slides that I show, that in ice you may actually have exchange between organics and water. But because, as you said, I think you answered your own question, that the abundance is significantly less, I don't think that is a main contributor. I think this is awful English, sorry. A main contributor.
Thank you.
Okay, good.
Very good. Please go ahead.
Okay, thank you, Paola, for a great talk. There was talk earlier in the meeting about the role of episodic accretion and luminosity bursts, both in the embedded and the disk phase. And so I wonder if you could comment a little bit about what that might do to the D to H ratio.
Yeah, that's very interesting. I can tell you what I think. I mean, that doesn't mean that that's the true story. What I think it can do is that you can, of course, for a short time, you can, say, evaporate and even destroy by sputtering, because I guess the outflow may also be, of course, more powerful during these short episodic accretion events. And then you reprocess this dust, and you may lower the deuterium fraction locally, but then you freeze that back. So this could mean that if this then becomes the main composition of the material that then will form the protoplanetary disk, you may already start there to decrease this deuterium fraction that we see, and then is then trapped in ice, and then forming bigger bodies that then we see in more evolved systems. So it could be a way of, say, starting the reprocessing, but keep it stored. So making in pieces, then you don't really, for a long time, say, have all this material in the gas phase and drop down to very low level the deuterium, but keep it at relatively large level. This could explain, say, our solar system. But don't take me too seriously.
Okay, very good. Please.
Hi, Paola. Jonathan Foster, Yale University. I was very interested in these hotspots of deuteration that you have in the that we see in the chondrites. Can you just speculate about why you get such a sharp contrast? Is that because there was a very sharp contrast in the D to H ratio somewhere within the protoplanetary nebula? Is there some real sort of phase transition, or is this something else?
I mean, I really like to speculate, but again, I mean, it's so. I remember talking with Scott Messenger about this, and at the end, I didn't really, so the theory I had, I think is not valid. But, I mean, it could be that these are some kind of, say, pristine material, maybe located within the rocks in a protected area, for example, let's say farthest away from the surface, where actually the heating and the reprocessing have not been very efficient. And so this, from a naive point of view, my naive point of view is that this really is preserving these tiny bits of pristine material that, of course, in these carbonaceous chondrites have to, in a sense, you should expect to not see much, because this is material that has evidently been reprocessed. So it's probably just like an island of peace in these rocks that then, form planets later on.
Any more questions on the balcony? I will ask the last question. So you showed you thought you were done. You showed a graph that shows the current value of D2H ratio in some of the new comets that agree with that of Earth. My question is that to what extent we are sure that what we know from D2H of Earth is actually primordial? The water on Earth might have been contaminated with biology of it during all these years, all these times. Is this, what you showed, is this conveying what it hopes to convey, or we still have to take it with grain of salt?
Yeah, well, I think that we need significantly more work to answer your question, so maybe you have to be a bit more patient than. But that's true. I mean, we have to take into account in all this processing of merging communities, we need to take into account all the processing that can happen, on Earth, and the fact that we were also the previous speaker was saying about the fact that you also evaporate and you tend to increase a little bit the deuterium. So, that could be done. I think you just we know the mass more or less. We know the mass of the water on Earth, and we know how long it probably stayed there, so maybe it could be a relatively, say, not easy, but calculation to do to see if that is consistent without any, accretion. But I say, why not, given that we know that we have been through this heavy bombardment, and we know that we have all these pieces of rocks containing water and this D/H ratio that, by chance, is exactly the same as, anyway, yeah, I agree.
Very good. Well, thank you very much. Let's thank our speaker again.